Hello everyone, welcome to the Epic Flight Academy. This is the Private Pilot Ground School course. My name is Mike Thompson. Remember, to be successful in this course, don't just listen to these videos. You also have to review Epic's online learning course and review all of this content with your flight instructor. Today's lesson is all about principles of flight. Well, in order to talk about the principles of flight and flying, we need to first study the atmosphere. The atmosphere is a blanket of gases around planet Earth. It's predominantly nitrogen, approximately 80%, and roughly 20% oxygen, with some other gases thrown in there. Now, this atmosphere is depicted here in this diagram. As you might guess, the air in the atmosphere is denser closer to the surface. The air is less dense the further we get from the surface. That's depicted by the number of blue dots here. The pressure at the surface, if we were to measure 1 square inch of surface and took it all the way up in the atmosphere, the weight of all of that air on that single square inch would be 14.7 pounds. Another way to look at that is all of that air pressure from outer space to the surface is enough pressure to push a column of mercury up 29.92 inches. That's why when you hear pilots talk about atmospheric pressure being 29.92 inches of mercury, that's what they mean. Now, in order to be able to calculate performance and talk about aerodynamics and use the atmosphere effectively to make calculations, we have to have a standard reference point. That's because as you go around the planet, the weather and the climate changes dramatically. When the weather and climate change, the pressure and density of that air changes. So it's very difficult to compare my aircraft's performance in South America over Brazil to its performance in Antarctica or Minnesota in North America. To make those comparisons accurate and to be able to talk about my aircraft's performance with some consistency, we use what we call a standardized atmosphere. The standardized atmosphere assumes that surface pressure is 29.92 inches of mercury and the surface temperature is 15 degrees Celsius. Other measurements for that would be 1,013.2 millibars of pressure, or 59 degrees Fahrenheit. In that atmosphere, the change in pressure from the surface to outer space can change dramatically with atmospheric conditions. Again, we have a standard reference point. In a standard atmosphere, we say that pressure changes 1 inch for every 1,000 feet. The temperature change as we go up gets colder and colder and colder. Again, that's going to vary dramatically depending upon the local climate and meteorology and weather. We use what we call a standard lapse rate. That is 2 degrees Celsius per 1,000 feet. Now, those changes in pressure and temperature vary dramatically. We use the standard as a reference point. Air, as we've discussed, is a fluid and has weight. Sometimes we don't think of that because the air is around us, we take it for granted, we don't really see it, but we have to stop and think, in fact, it is a fluid, it's got substance, and it's got weight. So we talk about air pressure and air density. The higher the pressure, the higher the density. The lower the pressure, the lower the density. Let's continue on with Newton's laws of motion. Now, to help us understand principles of flight, and in the near future, some aerodynamics, we need to discuss Newton's 3 laws. Here's the first one. Newton's first law: a body at rest tends to remain at rest. Okay, well that's me on the weekends. But then my wife needs me to get up and do some chores. I'm off the couch, I'm doing chores, and a body in motion tends to remain in motion and moving at the same speed in the same direction, unless it's acted upon. That's law number 1. Newton's second law: force is equal to the change in momentum per change in time. Now that one sounds kind of complicated. Force is equal to the change in momentum per unit of time. A simple way to think about that is force is mass times acceleration. So if I have a large mass and I want to accelerate it rapidly, I need a large force. Or if you look at it from the other side, if I have a large mass accelerating, that large mass accelerating will produce a large force. That's law number 2. Third law. Newton's third law says that for every action, there's an equal and opposite reaction. So 3 laws. First law talks about the body at rest. Second law talks about force equals mass times acceleration. And third law is the equal and opposite reaction law. Let's take a look at Bernoulli. Bernoulli was an Italian scientist, and he came up with this idea that if you take this fluid that we call air and you accelerate it through a constriction, its pressure and temperature changes. Now that's a pretty interesting idea. Well, here's an example of it graphically. This is called a Venturi tube. The Venturi tube is wide at both ends and constricted in the middle. As we move air through this tube, the air has to accelerate as it moves through the constriction. When it accelerates, the pressure drops. As it passes the constriction and slows down again, the pressure rises. So here's the air on the front end, forced into that constriction. It must accelerate to move through that constriction, and the pressure drops. What's not shown here is temperature. Remember, when the pressure drops, the temperature also drops.